Hi, my name is Tunjiri Susan, and I'm working with Chugun Sulaiman, and I'll be taking you through our project, which is Sparse knowledge distillation for electrogastrogram signal processing to predict diabetes. First of all, I'm going to start with a background and introduction. We are dealing with diabetes diagnosis, which is the early detection of diabetes, and it is critical for better management. Current methods are invasive and time consuming, and what you're trying to come up with is the non-invasive methods, whereby you're going to choose the EGG signals, electrogastrography recordings of the stomach electrical activity reflecting the gastrointestinal and metabolic health. And still, we are dealing with machine learning, and we're going to use advanced techniques like sparse knowledge distillation, which I'm going to be using as the case SKD, and it can help extract meaningful patterns from complex data. And our main objective for this project is that to investigate the EGG signals and to investigate using the EGG signals and sparse knowledge distillation to predict diabetes by analyzing gastric motility in the healthy individuals. We are mainly focusing on the identifying patterns in the fasting people and and the post-prandial states, which is like after consuming a standardized meal, and in this case, you are using the oatmeal project, and our goal is to develop a non-invasive real-time predictive tool for early detection of diabetes. And our literature review, we have diabetes prediction, which is early detection of type 2 diabetes through health parameters and biomarkers, which is so crucial. And then we have electrogastrograms, non-invasive recordings of the stomach electrical activity altered EGG patterns and are associated with diabetes, making them variable for diagnosing metabolic disorders. And next we have feature extraction, which is converts the raw EGG data to measurable features for analysis. And we also have signal processing techniques. You're going to use techniques like empirical mode decomposition, which is the AMD. I'm going to be using AMD, and filtering that helps to enhance the EGG signal quality, removing noise and artifacts for reliable analysis. And we also have genetic algorithm for feature selection, which helps optimize the feature selection by identifying the most relevant features for the EGG signals, improving the model performance and reducing complexity. And we also have machine learning. In this, we're going to be using different machine learning algorithms, such as like support vector machines and neural networks, which are trained on the extracted features from the EGG signals to like predict diabetes, and it will help us distinguish from the healthy and the diabetic individuals. And still, we are going to imply denoising because still, like I said, EMD and wavelet transforms removal noise from EGG signals, ensuring accurate feature extraction and improving the model accuracy. And like I said, sparse knowledge distillation, and this like helps transform knowledge from a complex model to a simpler one. Here, it reduces the computational demands and it helps us maintain the prediction accuracy, making it suitable for real-time and non-invasive monitoring. And our problem statement, we are mainly focusing on the computation problem statement, which is like the current diagnostic methods are invasive. This means they include blood tests and like other methods. And the main limitation for this is it cannot continuously monitor psychological changes in real time. When you want to implement it in real time, it doesn't give accurate values. And then we have technical challenges while using the EGG signals, like the noise level components that are present in the EGG signals and they require robust processing. And next we have high dimensional data. Feature extraction from the EGG signals is often like high dimension. This means it will require dimensionality reduction to isolate informative descriptors. And this will take more computation time because we have to like deal with the already extracted features from the EGG signals, and then we have to reduce the dimensionality. And what are some of the research questions and objectives? The research questions we are dealing with how can electrogastrogram signals be utilized to predict diabetes? Those are like the research questions we had to ask ourselves and like maybe people that we expect like people to like be with. Like we had to figure out like how electrogastrogram signals can be utilized to predict the type 2 diabetes, then the key features we are going to consider and that is going to help us differentiate.
Good morning. Hi everyone. So I've come to make some refinements in some work as we managed to produce something better, a little bit better. So we're starting with the methodology. I will pick up from where she left, my colleague. Starting with the methodology, we're going to acquire the signals, as you know about the topic already. We're going to acquire the EEG signals. We're going to preprocess them, that is, extracting the dominant frequencies that we're going to use in the predictions. Then we decompose them into most important frequencies. Then you extract features from them, from the frequencies that they pick from the individuals. Then you classify them and be able to classify them uh, uh, into diabetic and non-diabetic, which are diabetic patients. Yeah, we do this for all the models. We do this for all the models. All the models we between. So we between multiple models, okay, so that you can come up with a better performing model that is quite plain. Yes, so this is the visualization of the data. This will show you the most important features from the correlation, feature correlation, from this histogram kind of, it shows the feature correlation between the target and then the features. Yeah. So this scale will show you a negative and a positive, showing the most important feature and the least important features you expect. In this KD equate will show you it will tell the difference in the things in the mean, in the best of the mean of the diabetic, the non-diabetic, and then the non-diabetic in the data set. Yes. And then next, we're going to have the visualization of these three main features: the mean, the median, and then the standard deviation. That will show you where most of the data lies in this, because as you know, road EEG signals have tendencies of moving to negatives depending on the amplitudes. So this should show you the mean, the median, and then the standard deviation in that 3D spectrum. Yeah. Then we have box plots. Box plots, these are showing outliers, which individuals in the or which entries in the data set are far from the normal pattern. Yeah, depending on the features. So the features are on the x-axis, the watch, and then they show you the y-axis and as you know how the scatter plot shows, to show you which, as you see the dots far from the normal blue, then it shows that those are entries that are far from the point. Now we're going to the part. We're going to talk about the part where we train the models, where we actually train the models, and these are the results of the models, yeah, of the model performance. So we trained, we're going to train 6 models for the start, and we scaled it down to 6 models from the 12 that we had. So try to further study each one of them, and we are trying to get some output from them. So right now we start with this, or when you see the cursor is the decision tree model performance. So we first train the model on the original data set. So for each table, there is the performance, there is an output of of the matrices for the model in when it is run on regional data and when it is run on noise data. Remember, we worked this way. We're running, we're working on this research, but we also wanted to check whether the noise actually has something, has an impact on information on model performance, while while whether the noise will have an impact on model performance. Yes, we noticed that there is there is a change in the model performance, which might not be good because if you see in these tables, all the tables, it is showing that. So the first row will show the matrix name. Then the second row will show the performance of that model on original data, and then the third row will show you. I mean, the third column, sorry, will show you the performance of that model on the noise data. So it will tell this if you observe very well, it will show you that yes, the performance might have improved where it 1,111, but then we even notice that that could be because of what? It will be because of overfitting. Just reason because when you denoise, for example, numerical data, if you're not very keen and you are not working with with vast amounts of data, you might actually lose out on or useful information. So be careful while you're using. You might get better performance. You might seemingly get better performance, but this might be because the model is training on very small data. So it will give uh, output that is not in line. So for the second half, logic regression model, the logic regression model performance. So as you see, the claim for the logic regression is a little bit more for the original data and the first run. For the first run, as you see, it might be more. So we might not go with it. We might not go with it. Yes, the other performances are similar with the decision tree, but you might not go with it because it's time, it's training time increased a little bit. So you might opt for the other because of that. Then you go through the other models, base, which also has the less training time compared, which is roughly the same as the decision tree that we actually deployed. But the problem is that even its accuracy reduced, you know, even its AUC reduced compared to the what? Compared to the other cases here. So as we made the conclusion and implemented to use, we monitored them in the different cases and we show their consistency in performance. So as you see down here, it goes on fluctuating. So we wouldn't use the nine days as well. Then even the KNN model, then even the other model, the SVM, was a trained it and it also had that output kind of. So we were comparing whether you take that cannot be implemented in it here. So this is the decision configuration matrix for the what? For the model that is the decision tree, and it shows that it is not overfitting the load as it has an accuracy that is not 100%, but that can almost always give you the right precision. Yeah. Then you have feature works. What do we intend to do in the future? We intend to include that we intend to, diabetes is people who want to be able to tell these separate, to even go further and tell whether it's diabetes, type A or type B. So that's one of the feature works. We want to work with larger data sets. I told you it might affect the performance in the model. Then you advanced feature engineering, deep machine learning, want to go deeper, implement deep machine learning models, like CNNs, RNs, transformers, and all that. Then real-time monitoring, you want to be able to easily, for example, the way you put on a watch, and then it keeps on monitoring your heartbeat and all your heart rate and feel all that. So you want to be able to put it in a small gadget, for example, that can at all times monitor your performance and can actually tell you whether there is future possibilities that there is. Yeah, want to be able to, go that far. Yeah, so the limitations are data constraints. You don't have enough data sets. Data sets are very rare. Sometimes you have to simplify it a little bit. So you can train the models on a bit on a little bit bigger data set so that you don't overfeed, and then you can be able to work on bigger data sets. Then computational challenges training the teacher models. So this is mainly with the models that need a teacher and a student model. Yeah. Then generalizability and model performance may vary when applied in larger and diverse populations. Yeah. As you said, the need of the concerns, we work and train the models so that they are robust in the what? Nation side. So conclusion, the study made a thorough comparison of the different machine learning models that in the ability detection using signals for analysis, the decision tree was the best use. And we train this into under different scenarios when there is sparse learning, sparse knowledge diffusion, then them combined. So it was consistent in its performance. So that's what it showed. Significant outcomes. We apply the third order back. Thank you very much. That was it.